In the next set of videos, we'll be considering continuous time Markov chains or CTMC. And in this first video, we'll be looking at definition of continuous time Markov chains. Previously, we had considered discrete Markov chains, and we saw how all of that went. Here, we then come to that part where we look at Markov chains in terms of continuous time. So a stochastic process, which is a collection of x of t for time greater than or equal to 0, is called a continuous time Markov chain if the probability of x of t plus s is equal to j, given that x of s is equal to I, comma, all the past steps is simply equal to probability of x of t plus s equals j, given x of s equals I, and all the past states are not necessary. And this is of course exactly the kind of idea we had for discrete Markov chains too, because the Markov property says that every state before the present state does not matter in determining the next state. So the interpretation is that the future evolution depends only on the current state, not on how the process arrived at that current state. And then we refresh our minds about the idea of state space. The process takes values, that is, for a Markov chain, the process takes values in a countable state space. S is 0, 1, 2, and so on. And it can be finite, e.g. 0, 1, 2, and it can be infinite, uncountable, infinite countable, like for sets of natural numbers, 1, 2, 3, 4, 5, 6, and so on. Each value then represents a possible state of the system. Then we talk about the generator matrix Q. So it's a continuous time Markov chain is characterized by a matrix Q, which is Qij, and it has the following property: that every Qij is greater than or equal to 0 for I that is not equal to j, right? Then Qii is equal to minus summation j not equal to I for Qij. So every Qii is equal to negative of all the summations of every other Qij as far as j is not equal to y. Of course, qi means that I is equal to j, right? So the interpretation is that for qij is the rate of transition from state I to j, whereas minus qi is the total rate of leaving state I. Okay, so we then talk about holding time, which I think I've talked about when I consider discrete times or so, like that. So for holding time, the time spent in state I follows an exponential distribution t sub I. So it follows exponential distribution with parameter lambda I, where lambda I is minus qii. And the key property here is that the expected time of ti is equal to 1 over lambda I. This is what makes continuous time Markov chains memoryless in time. So then we go ahead to talk about transition probability function. So we had something like that also for discrete Markov chains, except that here the expression is different. So if you define probability of moving from I to j at a given time to be probability of x of t equals j given x of 0 equals I, then in matrix form we have that probability of t is the exponent of q raised to power t. So don't forget we had come across q at some point. It is the generator matrix Q. So that generator matrix Q is something that will be common in our discussions. So for the transition probability function for a continuous time Markov chain is the exponent of the product of the matrix x. This is the matrix exponential of Q, right? That's the exponent of the generator matrix Q multiplied by T. So, and then that takes us to the idea of Kolmogorov equations, which we are going to see in more depth as we go on. In separate videos, we'll be looking at Kolmogorov forward equations and Kolmogorov backward equation. So for the forward equation, it says that d dt of p of t. Don't forget p of t. We came across that p of t is the transition probability. So the rate of change of the transition probability for forward equation is equal to the probability at any given time multiplied by the generator matrix Q. Whereas for the backward equation, d dt of p of t is the memory matrix Q multiplied by probability at a particular time. So this actually describes how transition probabilities evolve over time. So transition probabilities can evolve in, in Kolmogorov forward equations or in Kolmogorov backward equations. And we're going to see these implications as we move on in this series of videos on continuous time Markov chain. So we have an example here for a two-state continuous time Markov chain. If you consider Q, being the generator matrix, to be -2 to 1 minus 1. So the interpretation is that so here we have two states, state 0 and state 1, state 0, state 1. So from state 0, to move from state 0 to state 1, like this, so it happens at rate 2. Then to move from state 1 to state 0, that is from this state 1 now to state 0, that happens at rate 1 here. So what we are basically saying is you have -2 to 1 minus 1. So you have Q to be -2 to 1 minus 1. So, and we're saying that there are two states. We can say state 1, 2, or state 0, 1. So in Python, counting starts from 0 most of the times. So if you're moving from state, so this simply means that this is P00, 0. Moving from state 0 to state 0, that's at rate -2. Moving from state 0 to 1, that's with maybe not Q, right? Maybe not P. I think it's better to use Q. This is like Q00, that is at state rate -2. Q01, that's moving from 0 to 1. That's like 0 to 1. Then this is moving from 1 to 1 at rate 1. I'm moving from 1 to 0 rather at state 1 at rate 1. I'm moving from 1 to 1 at rate -1. So that's what that simply talks about there. So, but then in this case now, it is based on the generator matrix that you get the transition probability, and that's the difference. We have for discrete, we have the transition probability, or the transition matrix, we have a straight, but here you need the generator matrix to get the transition probability. And now that one way to do that is you can use some algebraic. Of course, we need to get the exponent of qt, right? So if Q is -2 to 1 minus 1, like we have up here, we then want to get PT, which is the transition probability, and we are taking time to be 1.0. So P of T is the exponent, matrix exponent of Q times T, and then we get PT here to be this value. So we have this value here. So, from this generator matrix, we now have the transition probability, or the transition matrix, right? A transition probability function. So, yeah, generator matrix, right? So the exponent of the generator matrix multiplied by time actually gives you the transition probability function, or the transition uh, probability function actually. So now you have this result. Now, guess what? As time increases, this probability is going to stabilize at some value. So you can see so from what it was, it stabilized at 0.6. So if you take it to like 1000, whatever you get is like the equilibrium. So you can see the whole thing converges to 0.3333 and 0.66667, like that. So that's the concept here. So you use generator matrix to get the probability, to get the why do I keep forget? Transition probability function. Yeah. Okay. So then we talk about the interpretation. How do you interpret that result? If P at time 1 is 0.567, 0.433, 0.216, 0.7784. Of course, this is different. Now this is 0.366, 0.633. So, but based on that interpretation now, so then it means that starting in state 0, if you start from state 0, probability of staying in state 0 after time 1 is 0.567. So this is from moving from 0. Probability of staying in state 0. So to stay in state 0, that's moving from 0 to 0. That means staying there is 0.567. Probability of moving from 1 to 0, that is, if you're moving from 1 to 0, that is from 0, this is 0, 1. So probability of moving from 1, 0, 1. So probability of moving from state 1, state 1 to 0, that should be 0.216 here. Yeah, it should be 0.216. 0.216, like that. 0.216. Okay, but basically here, the results we got, I mean, this is it right here. So moving from state 0 to staying in state 0 is 0. The probability is 0.366 and all that. Moving from state 0 to state 1 is 0.63, blah, blah. Then moving from state 1 to state 0, that's 0.316. Moving from state 1 to state 1, that would be staying in state 1, actually, that's 0.3683 and so on and so forth. All right, but we discover that as time goes on, everything stabilizes around 0.3333 and 0.666667, like that. Now we then talk about the idea of the jump chain or the embedded Markov chain. So if you define Pij to be Qij over lambda I, where I is not equal to j, that is, you don't have Qii at any point in time, or you don't have Pii at any point in time. So in that case now, so you define Pij to be Qij over lambda I for I not equal to j, where lambda I now is minus Qii. Okay, so the example, we can now take an example of that, talking about jump chain. So for jump chain, for state 0, so if you have lambda not to be 2, for instance, all right, then P01 will be 2 over 2, following this formula now. So moving from P0 to 1, right? That will be this Qij. So Qij, if you take that to be Qij, I think it's still referring to this, I'm not sure. Qij. So okay, from 0 to 1, that's 2. It's this particular 2 now, following this matrix. And just like, I think it's basically the kind of thing I've done here. Q01, right? That is 2. That's 2 like that, using that same matrix. And then if we take lambda not to be 2, that means we have 2 over 2, and that is equal to 1. Then if lambda 1 is 1, so we have P10 to be Q10 over lambda 1, which is 1, and that is 1. Of course, Q10 is actually 1 from here. Q10 is 1, this particular one, like that. So in this case now, we see that the chain alternates deterministically, like that. The chain alternates deterministically. So then we can then talk about the simulating holding times. So to simulate holding times, you have lambda I, say lambda I is 3, and then you have the samples, and you do like 10,000, and then you get the mean at the end of the day to be the 0.333 as the holding times. Then the holding time simulation now, we simulated a time which is exponential with parameter lambda equals 3. The theoretical mean is actually 1 over 3, and 1 over 3 is roughly 0.333 something, and that's why as you keep running this particular code, you keep getting 0.3 something something, so it just keeps hovering around 0.33333 like that. So, and here now, if you want to, the sample mean should be close to this value, of course. That's why you see the sample mean close to 1 over 3, which is 0.333. So then talking about simulating a CTMC path now. So, if you run this, we're taking time to be, if you start from the 0 times 0, and maximum time is 5 with that generator matrix, -2 to 1, -1, and do all of that, you end up getting, see what you end up getting here. So you get 0, 0 first, and then you have 0, 2, 4, and everything just keeps going like that. So you keep running, and then you keep getting different values like this. So these are possible paths that the CTMC can take. So it can expand, it can shrink, and the values just keep going like that. So you see the state just keeps alternating from 0, 1, 0, 1, 0, and all of that. So, it expands, it shrinks, and so on. Then we talk about the distribution, the stationary distribution. Now, for discrete Markov chains, the stationary distribution we found to be pi p equals pi. But here, since we're talking about continuous time Markov chain, CTMC, so the stationary distribution, a distribution pi satisfies pi q equals 0. That is pi multiplied by the generator matrix equals 0. And the summation of pi I, just like in the case of discrete, is always equal to 1. So in this case, if we do that here, with this, we get -2 to 1 minus 1. So for QT, you end up getting 0.33, 0.67. And that is the same thing that happens as you keep simulating what we did the other time to get P of T. If you keep doing it, you converge at this point now. So this is like the equilibrium point. Now, this is what has happened. -2 to 1 minus 1. This same one here. So you have Q -2 to 1 minus 1. So we are saying that pi Q is equal to 0 in this case. So that means that pi now is that's pi 1 pi 2 like this into minus 2 to 1 minus 1, and all of this is equal to 0. Okay, that's like 0 0. What are we going to get? This is 2, this is 1 by 2 matrix, this is 1 by 2 matrix multiplied by 2 by 2 matrix. So when we do this, it's going to give us a 1 by 2 matrix still. Okay, so that means this is going to be 0 0 like that. So now, with this in place, now you just have this is one row, so you just write each one twice. Each one once, minus 2 1, and then minus 2 1 and 2 minus 1. Then you put pi 1 pi 2 over this, pi 1 pi 2 over this, and all of that is equal to 0 0. So we then have so if you tidy things up, you get minus 2 pi 1 plus pi 2, then 2 pi 1 minus pi 2, all of that equals 0 0. Okay, so I have a hunch that each one will translate to the same thing, because minus 2 pi 1 plus pi 2 is equal to 0. Start from this one. So that means that pi 2 is equal to 2 pi 1. We have that expression. On the other hand, we can also have 2 pi 1 minus pi 2 equals 0. So that simply means that, again, pi 2 is equal to 2 pi 1. If you transfer pi 2, it's also, so it's basically the same thing. So what you then do is, from pi 2 equals 2 pi 1 now, you can then recall that pi 1, that plus pi 2 is equal to 1. So in that case, now it means that pi 1 is equal to, it means that pi 1 is equal to 1 minus pi 2. So with this in place, then you can substitute back. You can say, so pi 2 is equal to 2 into 1 minus pi 2. So that pi 2 now is equal to 2 minus 2 pi 2. So if you collect like terms, you have pi 2 plus 2 pi 2 is equal to 2. So that then have 3 pi 2 is equal to 2. And then pi 2 now is equal to 2 divided by 3. So pi 2 is 2 divided by 3. So that means that pi 1, which is 1 minus pi 2, will simply be 1 minus 2 over 3, which will be 1 over 3. 1 over 3. Okay. So finally, so then pi 1 pi 2 is equal to pi 1 is 1 over 3, pi 2 is 2 over 3. And of course, that's approximately 0.333, if you like, and 0.67, because if you add it, it must add up to 1. So that's why we have that particular result when you simulate like this. So that's why you have 0.333 and 0.667. In summary, what we have done so far is this, that um summary of continuous time Markov chain. A continuous time Markov chain is defined by a countable state space, number one. Then the Markov property, of course, the fact that this state determines the next state. Previous states before this state do not matter in determining the next state. Then we talk about a generator matrix Q, and then we talk about exponential holding times and transition probabilities, with this relationship that the transition probability is equal to the exponent of the uh, generator matrix Q multiplied by time. And then we have the long run behavior given by stationary distribution. So the intuition here is that a continuous time Markov chain waits for a random time and it jumps to another state, and this repeats indefinitely. So we have practice problems which you can try out based on the ones I've done, the ones we've seen up there already, and you can also reuse the codes or modify the code sometimes to do some of those things. So this one says define the continuous time Markov chain and state the Markov property mathematically. Of course, we have all of that up there. Explain the difference between the discrete time Markov chain and the continuous time Markov chain. One big experience I've seen, difference is that in the discrete time Markov chain, you just have the transition probability, the probability transition matrix straight up, but for continuous time Markov chain, you get the probability transition probability function. You get that from a generator matrix Q, right? So given the generator matrix Q, explain the meaning of Qij for I not equal to j, and Qii, all of that we talked about before. So show that for any generator matrix Q, each row sums to 0. Okay, for every generator matrix, each row has got to sum to 0, and that's why you saw 2 minus 2 and minus 2, minus 2 2 and minus 1, minus 2 2. Yeah, this is what I'm referring to, by the way. So for every generator matrix, right, each row has to sum to 0, whereas for every probability density probability for each transition matrix function, the every row sums to 1. So minus 2 plus 2 0, 1 minus 1 0. So that's what happens for generator matrices. Each row sums to 0, but for the probability, each row sums to 1, like that. So generator matrix and rates now. Determine whether the following matrix is a valid generator matrix. Of course, minus 3 plus 1 plus 3 is 0. 2 minus 5 plus 3 is 0. 1 1 minus 2 0. So this is a valid generator matrix because every row sums to 0. So for the matrix in problem 5, compute the rate of leaving each state. Of course, the rate of leaving each state, um, that those are the Q minus QIIs, right? So that would be like, so the negative of this. So the rate of staying in the state is minus 3. So to leave here, that would be minus Q11, that's 3. Then to leave state 2, the rate is 5, that's negative of minus 5. The rate of leaving state 3 is minus 2, which is 2, like that. Because the rate of leaving each state is minus QII, because QII is the rate of staying in the state. So for the same matrix, compute the expected holding time in each state. So we can also do that based on what we saw already. You can use the matrix, the code to Python code. Transition probability. Define the transition probability function Pij of t. Show that P of 0 equals I, and then write the formula for the transition matrix in terms of generator matrix. Of course, that's simply E raised power Qt. Then we have the Kolmogorov equations, which I say we are going to deal with better in separate videos later. Write down the forward Kolmogorov equation. Of course, this one says that d dt of P of t is equal to P of t multiplied by Q, whereas the backward Kolmogorov equation, d dt of P of t is equal to Q, the generator matrix, times P of t. So for forward, you have P of t, P of t multiplied by Q, but for backward, you have Q multiplied by P of t. So then we have jump chain, define the jump chain associated with a CTMC, right? And then we have given Q to be this, compute the jump chain transition probabilities. Of course, you just need to find the exponent of this matrix times a given time. Maybe you can take time 1, and as the time gets big, the probability stabilizes at some point, like I showed you the other time. And then you have computation problems. Given Q to be this, compute lambda naught and lambda 1. We saw all of this before. Then for problem 16, compute the expected holding time in each state. So with lambda naught and lambda 1, you can then compute. Let's even see how do we, yeah, lambda I. Okay, lambda 0 will be minus Q00. Lambda 1 will be minus Q11. Lambda 2 will be minus Q, all of that. So I think this is, the lambdas are pretty straightforward, just like what we did before. So here now, so lambda naught will just be minus Q00. That's minus minus 1, which is 1. Then lambda 1 is minus minus 3, which is 3. So for problem 16, compute the expected holding time in each state. So we can then do the, I think this is now 1 over 1 here, which is 1, and then 3, this 3 now over, or is it minus 3 now over lambda 1? No, I think it should be the formula, right? 1, I think it's 1 1 or so. So okay, this will be 1 0 over lambda 1, so which is still 3, like that. So for stationary distribution, you have defined the stationary distribution pi for a CTMC. So that was exactly what we did the other time. So we saw for pi such that pi q is 0 and pi naught plus pi 1 is 1. So that was where we got that pi naught, or if you like pi 1, pi 2. Here they use pi naught, pi 1. So pi naught is 1 over 3, pi 1 is 2 over 3. Then the conceptual, which is advanced, I'll explain why exponential holding times are essential for the Markov property in a continuous time. So you can refer to what we did initially. So with this, we come to the end of this interesting video about the definition of continuous time Markov chains, which is pretty interesting. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and subscribe right right now, so that you can always get alerted, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can of course become a member of this channel by clicking on join, and that gives you some special privileges you find out as you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.